Okay, so now here's the second part, and this is where we're going to show that the span of B hat is the same as the span of B. Now, that's what we want to show. Okay, so we need to show this relationship here. Now, showing that the span of B hat is contained in the span of B is easy because we can write any member of the span, right? Any member of span B hat, right? Okay, as this, because we can take this and just substitute in, just like in the previous video, the first half of the proof, right? And what do we get here? This is a linear combination of linear combinations of members of B, and hence has to be in the span of B. Remember the linear combination lemma, right? So that part is easy and done. Now, for containment in the other direction, recall that if vector V is equal to this, right, with Ci not equal to 0, right, that's one of our assumptions, then we can rewrite beta sub I as this linear combination, right? So keep that in mind. So we can rewrite beta sub I as this linear combination involving V, right? Okay, and why? Because C sub I is not equal to 0, so we can do that. And now consider any member of the span of B, right? So here's the D sub I, any linear combination, right? So in the span of B, we can now substitute in up here for B sub I. Okay, and so what happens? When we do that, we get what? We get a linear combination of linear combinations, just like before. So when we recognize that, then that tells us, by the way, it's a linear combination of linear combinations of all the members of B hat. Okay? And hence it's in the span of B hat. And we're done. And that finishes that half of the proof. So we just proved the two things we needed to prove. We needed to prove that B hat was linearly independent, which we did in the last video, and now we just proved that the span of B hat is equal to the span of B, and that's all we needed to prove the lemma.